thank you for joining us this morning as we prepare to discuss the rise of the chiplet. My name is Brian Bailey, Technical Editor for Semiconductor Engineering. Prior to my career as a writer, I was Chief Technologist for Functional Verification at Mentor Graphics, now part of Siemens Digital Industries. While I have 30 plus years of experience designing and building verification tools and methodologies, I started off designing aircraft control computers. It's my pleasure to be the moderator for today's webinar. Chiplets have certainly caught the imagination. They may provide an avenue to enable the continuation of Moore's law, not on a single monolithic die, but by building functionality on multiple dies and integrating those within a package. This can help to increase yield, make systems more modular so that they don't all have to be redesigned at the same time, allow the best fabrication technology to be used for each piece of the system, and even perhaps in the future to reduce total system cost and enable chiplets to be purchased in a third-party market. There are several hurdles and problems that need to be solved before this becomes a mainstream technology. However, the possibilities are endless, and leading-edge companies are beginning to establish the course for the industry. Standards are being considered and put in place so that hopefully it will not be the same Wild West that was created when soft IP first became an important part of the industry. Joining me today are Nick Iliadis, Senior Director of Product Planning at Achronix. Prior to Achronix, Nick was VP of Portfolio and Technology Strategy at Marvell Semiconductor and Vice President and Group CTO at Broadcom. Rick Wozniak, Principal Analyst for ASIC and SoC at Semico Research. Rich has been in the semiconductor industry for 35 plus years, looking at analog, ASIC, memory, and processor functions, as well as system products, software development, and process technology. And then Bapi Vinokata currently leads the Open Domain Specific Architecture sub-project within the Open Compute Project. The ODSA has active volunteers from over 50 companies and has 8 active work streams that aim to define an open chiplet marketplace, and has several key chiplet-related activities in flight that are essential for establishing an open chiplet economy. So the structure of today's event. We will provide a brief overview of the chiplet market and how it's evolving. I think we will see some controversy starting even as we do that. I do have a few questions to get the discussion going, but we want to hear your questions. For those of you watching on LinkedIn, just enter your questions as comments. Somebody will be monitoring those and may feed them into the platform so we can address, we can address some of them live. We can address them live rather than waiting until the end when the context may be lost. So please do put in your questions when you think of them. The webinar is being recorded. So if you want to go back over it or share it with a colleague, that's possible directly within LinkedIn. So enough from me. Let's get started. Rich is going to provide us with an overview of what chiplets are and how they are being used today. So take it away for us, Rich.
Thank you, Brian, and thanks for everyone joining us today. We appreciate it. So what is chiplet technology? Basically, it's a micro electronics design and a manufacturing approach different from designing monolithic parts, where multiple smaller dies or chiplets are combined into a single package with each of the chiplets performing a specific function. This allows a mix and match kind of an approach, where everything doesn't need to be at the same geometry. There can be older geometries or cutting edge geometries. Depends on the application. The chiplets are connected together to form an SoC-like solution. And this approach allows a greater flexibility, scalability, and cost savings by using different off-the-shelf chiplets rather than designing and manufacturing custom parts for each iteration. And the chiplet approach enables a combination of functions that are not process compatible. So, for example, you could think of adding silicon photonic capability to a monolithic part. Very difficult to do, hasn't really been done that much. Now it would be possible. Next slide, please. So chiplet market landscape today. What is driving the move to chiplets? One of the major contributors to this emerging technology is the fact that companies that have very large monolithic designs, especially at the cutting edge geometries, are seeing very poor yields. And so, for example, a design at 5 nanometer, 300 square millimeters, roughly the max yield you can get is about 50%. And as the die area increases beyond 300 millimeters square, the yield gets worse. So there's a cost issue. The chiplet approach avoids the reticle size limitation that people are bumping up against, and it makes a big leap in performance possible for these kinds of approaches. And we believe, and Semico believes, that this is going to lead to a great deal of architectural exploration and innovation. AI market is one example. I mentioned silicon photonics. There's a whole host of different things that can be done, and we'll show a few examples in upcoming slides. The chiplets can disaggregate large designs into smaller pieces. Known good die will take the place of many of these disaggregated functions, and those will be more or less standardized parts that you can buy off the shelf. Although not finalized and currently not bidirectional, the Universal Chip Interface, the UCIe standard, ties the chiplets together within the package and allows for downshifting speeds. There are many other interconnect technologies that are being explored. PCIe, CXL, bunch of wires, and others will probably surface. So there will be a range of solutions available to the design community. And currently there are chiplet solutions available from Intel through their Altera product line, AMD through their Xilinx product line, and NVIDIA. Next slide, please. So it's our belief, Semico's belief, that it's going to be 1 to 2 years before you can order chiplets off the shelf. And by this, we mean a complete solution from multiple vendors, not custom solutions, kind of industry standard solutions that people will develop for a range of applications. And as Brian mentioned at the beginning, there will be a little controversy over this and a lot of debate. Next slide, please. So, challenges to overcome. It's our view that the issues that the industry has worked through over the last 30 or 40 years, things like testing, reliability, rework, packaging, qualified vendors, supply chain logistics, EDA tools, and IP products, are now going to have to be rethought and reworked through in view of the chiplet introductions. And it's so instead of 40 years or 30 years, we're going to have to do this in 2 or 3. So the upshot, the good news is we're going to look at the solutions, the previous solutions that have been worked through, and use those as templates to apply to the chiplet market. So it probably will cut down the time that is necessary to rework these issues. It's not clear if HBM or other memory types will incorporate UCIe on chip. This, the current memory products, discrete memory products, all have industry standard interfaces. UCIe is not an industry standard yet, and the DRAM suppliers are going to have to decide whether to incorporate UCIe as an interface on their parts, and it's going to depend on the volume opportunities and who the customers are going to be. So this is something that needs to be determined. Any known die intended to be connected via UCIe needs to be redesigned to include the interface, and realistically none exists today. So there's a process that is going to have to be gone through to incorporate those interfaces on the parts. Who assumes the liability and the cost for failed chiplets and a packaged chiplet? Small packaging companies may not have the financial resources to undertake large volume opportunities. So there needs to be some work done in this area to smooth the path, so to speak, to allow some of the smaller packaging companies to participate. Next slide, please. So we believe the field is wide open today for companies with innovative ideas and solutions to overcome these challenges. No one company has a corner on the market for good ideas. We've seen that in the AI market, the emerging AI market today, where there are a host of companies that have different solutions and are exploring different architectures to come up with the right one for specific applications. And we believe the same is going to happen for chiplets. Next slide, please. So predictions and opportunities. Semica believes the market inflection point is going to be reached when solutions are found for these previously mentioned issues and are widely available in the market. The market volume hits when those companies with smaller designs, less than 100 square millimeters, let's say, adopt chiplets. That's going to happen when they feel comfortable that these issues have been solved to a reasonable extent. The chiplets enable these smaller companies with limited resources to do things that were previously not possible to them, such as adding silicon photonics or robust security functionality, AI accelerators, and a host of other functionality. Semica believes this capability is going to further accelerate the use of eFPGA gates in these designs due to their ability to enhance the functionality of the products. Semica believes embedded analytics from companies like Proteantex, Synopsys, Siemens, also called silicon lifecycle management products, are going to be used in chiplets. Predictive maintenance, power, and voltage monitoring, fine-tuning memory processor interactions, and things like that are all possible through the use of this technology. We're seeing a lot data center operators and hyperscalers starting to adopt this technology because the uptime is crucial for their businesses and their business models, and it makes sense to do this. We think the same approach is going to be applied for chiplets. There's also the possibility for the use of CPU functional accelerators placed around the chiplet package to enhance different types of functionality. And it's likely that these designs are going to be either ARM-based or RISC-V solutions. Low bandwidth functions like analog can be connected to via UCIe, but may not be the most efficient solution. So that we believe there's a possibility for another interconnect technology just for this case to maximize performance. Next question, please. Next slide.
We may want to pause here. We have quite a few comments coming in regarding the different standards. And I think that we're trying to be agnostic here of different standards. That's why Boppy is here. Boppy is representing ODSA. So we don't want to say UCIe or a bunch of wires, either one. I think we want to talk about either one being an enabling technology and having the designers, the chip manufacturers decide which one they want to choose based upon the attributes of either one. So I think the UCIe versus a bunch of wires, I think that debate should not be had here at this point, because I think we really want to look at the chiplets as a whole, and rather looking at whether it's a bunch of wires versus UCIe. And I think Brian also made a comment about UCIe not being bidirectional. I think what he meant there is that that it has a transmit and receive, but would there be more flexibility if it was actually a bidirectional nature, meaning that each pin could either be a transmitter or receiver?
And we're certainly going to give Boppy the opportunity to talk about what's going on within ODSA. So we are certainly going to address that. And as I said at the beginning, it's almost everything here is controversial at the moment. It's none of this is established yet. The industry will decide. So
Right.
we need to make sure that there are multiple things out there that they can choose from and decide the real winner for the industry. Were you done, Rich, or did you have more that you wanted to say?
Well, just in general, chiplets are going to allow new types of functionality and performance in smaller footprints than was previously possible. And we think that that opens the door for a lot of architectural exploration and a lot of innovation, a lot of ingenuity is going to be applied to these things. So we think there's going to be a great leap in performance and functionality possible through the introduction of chiplets. So here's three examples of simple architectures that people have talked about. This one, as it says, just a simple architecture. It has the HBM memory incorporated into the package with the controllers. There's a NOC fabric on the core compute resource chip. Embedded analytics, EA stands for embedded analytics. And there's a security data plane processor with a CPU functional accelerator and an IO hub with different interfaces included. Next, please. This is a more advanced architecture, more memory, more core compute resource chips. Again, this includes a security data plane processor and an IO hub, but now it adds silicon photonics as a chiplet for functionality for higher transmission speeds. And next one. And this is a kitchen sink kind of view where I tried to pull in just about everything that could be done as far as in one package. I do not believe that this is ever going to see the light of day. It's not something that people would manufacture, but I believe indicates what would be possible to do. So again, we've got silicon photonics included, a security data plane processor, eFPGA gates in a chiplet, embedded analytics, analog functionality, RF, a global clock might be used initially, but eventually we think that most, if not all of these parts are going to be self-timed. So you could remove the global clock, non-volatile storage, AI acceleration. So this is a whole range of different functionality that could be done depending on the application and the market requirements.
So,
I think
Rick,
you had some.
sorry.
Go
I see
ahead.
I see you have an eFPGA up there in the upper right-hand corner.
Right.
This is actually near and dear to my heart. I actually presented about this a couple weeks ago at the Chiplet Summit. Can you move the slide forward one, please? Yeah. So Achronix's approach here is that we license our FPGA fabric and our 2D NOC as IP. We not only use it for our own products, but we also license it as IP to other designers, people that want to build chips that have an FPGA element within them. But we're also, developing, our own chiplets as we move forward, and we are now able to license the solution as IP to customers that want to build their own FPGA-based chiplet. And we are agnostic to whether it's UCIe or a bunch of wires. That is a choice of the designer that's going to use this IP. But we've got the mechanism in there to basically have what we call a gasket, a shim that goes between the die-to-die IP and our fabric and NOC, such that you can attach it to basically either a UCIe or a bunch of wires, which seem to be the two major standards that are out there today. What we're seeing between UCI and a bunch of wires obviously is out now with some test silicon and got some traction. But UCIe has a lot of companies supporting it. UCIe also supports what's called an advanced packaging, so you get a higher bandwidth density per millimeter squared. So they both have their positives. I'm not sure negatives, but they both have their positives. Brian, sorry, you were going to say something.
No, thank you, Nick. But at this point, it's going to be a great opportunity to go back to our first question. And ODSA definitely has been looking at a bunch of these issues. So, Bobby, what is needed to enable chiplet adoption that you're seeing?
Right. So the ODSA, I'm here representing a large group of active volunteers. So I'm here. This is sort of a distillation of everyone's thoughts. When we're starting, the way we're looking at it is roughly 2 or 3 things, right? One is you start with the premise that chiplets will be everywhere chips are eventually, right? It doesn't matter where we're starting, but eventually that they will be everywhere. Now, if you look at this chart, you'll see that roughly, there's a fairly significant markets for semiconductors in various applications. And the thing that strikes you is that there is almost 2 orders of magnitude difference in power requirements, in bandwidth requirements, computing requirements, and even in terms of the non-computing functional requirements, right? So if you look at all this and you say, can really you need a really adaptable standard or a collection of standards to meet this diversity of requirements, right? So that's one thing you have to look at when you're looking at saying what will it take to get chiplet adoption. You need to serve a fairly broad, diverse set of needs. Next slide, please. The second thing to understand is that chiplets will change the current business and technical workflow in the value chain. That things which a designer didn't previously need to recognize, like packaging technology, have to be brought forward into the design process. The second thing a designer may have to consider is, if I'm designing a chiplet that works with 4 other chiplets, what's the lifetime of those other chiplets? Will they match the lifetime of my product? Or will I have to replace one of those chiplets while my product is live in the market? So things like inventory and lifecycle management, which a designer really didn't need to worry about, have to be brought forward into the design process. So in some sense, you need to recognize that chiplets will change the workflow with product design. Next slide, please. So one of the things we've sort of started talking about is, rather than thinking about it as a marketplace, which sets up this abstract that, I'm going to buy something off the shelf, and that's a much harder challenge. We started thinking of it in terms of a chiplet economy. What will it take to build and that chiplet economy doesn't need just standards, but it needs workflows, it needs tools, so that a company can build a chiplet-based product either by buying some chiplets from outside companies, buying tools to support chiplet design, buying or learning from the community with prototype designs. And in some sense, as one of the questions asked, and as Nick said, right, the chiplet economy is already here in some portions. You can buy complete designs which support a bunch of wires interface. There is now a open specification to physically describe chiplets in an XML format. So there's a bunch of things the way we're thinking about it is as a chiplet economy. And so if you go to the next slide, please. So when you look at it as a chiplet economy, it becomes reasonably clear that the problem of designing with chiplets and the standardization and the efforts needed are not just at the interface, though that attracts a lot of attention. You have to provide tools and mechanisms for SIP design. You have to provide tools and mechanisms for SIP integration, technical workflows, right? So one of the simplest things is, how do I describe a chiplet? And in the OCP, we've just had an announcement with JEDEC where a format developed within the OCP from one of its member companies is now going to be a part of a JEP 30 part model. That whenever you make a chiplet, that's how you start describing it. So on this slide, I'm not going to go through each of these line items, but they give you a sense of the problems to be solved if you're trying to design with chiplets. So, for example, we already touched on the known good die, or what does a business contract with chiplets look like, right? And what do logistics with chiplets look like? And I'm happy to say that in the OCP, we have work groups doing each of these activities. As an example, there is a worksheet that is available to the general public today, where you can go and download, which helps a designer compare a chiplet-based design with a monolithic design. It includes parameters for design costs, for manufacturing costs, for different heterogeneous process nodes, etc. Or we have reference tools to help you compare multiple die-to-die interfaces out in the market today. And we're also building things where, one of the hardest things to do is to get started, is to learn how to build stuff and how your processes change. So we have a lot of reference projects. We're going to do a demonstration from a bit of an open package that connects die from two different companies. So the way we think about it is that you need to do a collection of activities, all of which together help companies get into the chiplet economy, but they're not overly specified. That we'll do a core set of activities that the marketplace will take and adapt to various applications.